Hello, everyone. Welcome to our live session for Friday, February 25th. It's been a few weeks, so we are excited to be back. We have lots of people joining us today. We're looking forward to all of your questions. Reminder, please post your questions in the chat. I will grab them from there. We try to pick a variety of topics, and we try to go generally in order, but we also try to pick a variety of topics and a variety of questions or questioners. So we are going to get started. Chris, I will let you say hello to everyone, and then we'll get started.
Okay, welcome everyone to live Q&A session for the online course, or anyone else who found us a different method. Took a few weeks off. I was on a cruise actually, as the Viking resident astronomer, which means giving a lot of lectures, and they have a planetarium dome on the ship, in fact, and so I gave like 21 sky shows and 5-star parties and so on. So fun, but quite a lot of work. So happy to take your questions on astronomy. The floor is open.
The first question is from one of our live participants. Eleazar Santos asks, what are your expectations regarding the possible discoveries with the James Webb Space Telescope?
Any telescope of that capability, the largest telescope we've ever put in space, working in a different wavelength regime from the Hubble, sort of near infrared, is going to discover things that we can't anticipate. That's the fun of astronomy, that a lot of things are pure discoveries that weren't anticipated. But in the realm of things that we could anticipate, because these are the scientific objectives for the telescope, I can imagine that it's going to detect extremely early galaxies in the universe, essentially the first wave of gravitational clustering that produced stars and galaxies, and perhaps the first black holes in the universe, embedded in dusty disks and shining in infrared light. So that'll be interesting. It's also going to study exoplanet atmospheres. That's very difficult work for any telescope, even for James Webb. And so it may find ingredients in the atmospheres of exoplanets, super Earths, for example, that we don't anticipate. That would be an interesting surprise. And just generally, when it does survey work, it's going to find perhaps new categories of objects that we haven't anticipated. So it's always difficult to predict discoveries because history is full of them.
Excellent, thank you. The next question is from another live viewer. Lawrence K. asks, I understand quantum gravity contemplates particles called gravitons. If so, how do these particles escape a black hole? Are they traveling at greater than light speed?
So gravitons are a construct of particle physics. The standard model of particle physics associates an exchange particle with each of the 4 fundamental forces. So analogous to a photon for the electromagnetic force, you would have a graviton for the gravitational force. Gravitons have never been directly observed, so we don't observe an exchange particle carrying the gravitational force. And in fact, general relativity has a rather different conception of gravity in terms of curved space-time and doesn't use the graviton concept. So at the moment, a graviton is an unobserved hypothetical particle that does come out of quantum theory, and indeed would travel at the speed of light if you could observe it. And in the context of a black hole, yes, the graviton is essentially retarded to never escape, and so will be reduced to a standing wave. But that, again, has not been confirmed by experiment.
All right, the next question is again from one of our live participants. Demetrius asks, let's see. Do you expect that JWST will capture a firstborn star, population 3? Which are the limitations we are dealing with? Which are the limitations that we are dealing with, that they are so far back in time or that they are so short-lived?
So the issue of population 3 stars is an interesting one, and indeed James Webb Space Telescope was designed to be able to detect that. The population 3 star refers to the first generation of stars that form in the early universe, perhaps within the first 100 million years, as gravity starts to form the first structures. These stars, in theoretical calculations, form in a mass range that's larger than stars in the present-day universe. It's possible these stars go up to 200 or 300 solar masses. They, of course, also are formed purely from hydrogen and a little helium, because there's no heavy elements yet being created. And the stars' behavior and their lifetimes are different because of their chemical composition. They're very short-lived, of course. These massive stars, they form early and they're very short-lived. So even the James Webb will have trouble pinning down population 3 stars, partly because its field of view is small. So even though it has great reach back in time towards this epoch, the field of view of its detectors is small, and so if these stars are rare in their first incarnations, James Webb may just not be able to survey enough sky to find them. So it's an open question whether James Webb will detect population 3 stars.
The next question is from Parth Sarda. According to famous physicist and philosopher Kuhn, science has 3 phases. First is the normal phase, which is followed by crisis and scientific revolution. So which phase is our current phase?
Well, the Kuhn paradigm of how science works, has had some pushback over the years. It was put out in the 1950s and is very influential. And it does indeed describe some historical circumstances of how science has evolved. It's not clear that astronomy is in a crisis or a pre-crisis phase. There's indication that our cosmological model is not fully robust, and some people have claimed that this is a crisis. There's possible indication that our lack of understanding of dark energy and dark matter also amounts to a crisis. And it really reflects the fact that our models of physics are still incomplete. So it's not clear that you can call incomplete models that you know to be incomplete for well understood reasons to be a crisis. It just means you haven't finished doing the work. You haven't finished building the theories that explain the universe you live in. A crisis would be if one of the well-accepted theories, such as general relativity, was found to be wrong or just going in the wrong direction, and there's no indication of that yet. So although there's a minority view that astronomy, astrophysics is in a crisis, a Kuhnian crisis, I'm not sure I agree with that prognosis.
Excellent, thank you very much. The next question is from Wendy Traver, who sent an email asking, in a multiverse, wouldn't other universes have their respective cosmic microwave backgrounds that we might be able to detect or might be interacting with ours somehow?
Well, in a multiverse, if these other parallel universes had similar genesis and evolution to ours, in other words, they had hot big bangs of their own, then yes, they would have their own relic radiation, like the microwave background. The trouble is, in a multiverse concept, the space-times are distinct and they're non-interacting, and so there's no observational imprint of another parallel universe into our universe. The slight exception to that is in terms of gravitational radiation. So there's a possibility in some of the multiverse models that gravity waves from one space-time can imprint on another space-time. So that would be the signature rather than microwave background.
The next question is from Faisal, who's on with us live. And I believe I understand the question, but you can correct me in the chat if I'm not quite right. The question is, are dead planets or dead moons and asteroids possible to detect from any electromagnetic signal? And I'm not sure if they mean in the solar system or extrasolar, dead planets, dead moons, and asteroids. But we can talk about sort of both eventualities.
Well, if by dead you mean inactive or not geologically active, so in other words, if there are planets or moons, they would just be cold rocks with only mild radioactive heating. If they're beyond our solar system, yes, we do have ways to detect them through the usual methods of the Doppler shift, reflex signal, and through the eclipse method that the Kepler telescope proposed and did very successfully. So we do have methods for detecting essentially dead rocks, moons and planets in space. They're indirect methods that use their gravitational influence or their occulting of the parent star. And that's a standard mode by which we detect all moons and planets.
So the next question is from one of our live participants, World of Science. Can you elaborate on what, in essence, would count as perfect evidence for a discovery of an object of cosmology. And I'm not sure exactly, but maybe we can talk about like what are some perfect, in a perfect world, how would we detect something like a black hole or an exoplanet or a star or another galaxy, something like that.
So the criterion in astronomy, just in very general terms, for detecting something, that's an important distinction to make. Well, what does it mean when astronomers say they've discovered or detected something? The typical criteria, taken by analogy from physics actually, is that in terms of a signal above noise, the image above noise or a spectral signature above noise, is that it be 5 sigma or 5 standard deviations above the noise level of background. And that means the odds of it being a false discovery are a few parts in a million, so it's very unlikely to be a false discovery. So astronomy tries to hold to the 5 sigma criteria that's also used in particle physics. That was used, for instance, for the Higgs particle in 2013 and 2014 to show that it had been actually detected significantly. Sometimes an initial result is published at the much less impressive significance level of 3 sigma, which actually gives a slight chance, a fraction of a percent chance, that the discovery is in error and is a fluke or a fluctuation. And occasionally astronomers have been burned when they use the 3 sigma level, so they therefore tend generally to use the 5 sigma level, which is pretty gold-plated.
The next question is from Maurice, who's on with us live. I believe that just as galaxies devoid of dark matter have been discovered, there may also be parts of the universe where time passes differently and the speed of light is faster or more slowly. What do you think of the possibilities of something like that, and how would we be able to detect it?
So I'm not sure that we've seen that kind of radical variation in physics. The fact that we found some galaxies that are devoid or have extremely little dark matter is certainly interesting. It just speaks to a particular history of that stellar system, and probably where an interaction means the dark matter envelopes have been stripped off and we see the baryons without any corresponding dark matter. So that's a particular astrophysical history. Now that is in a different category from the idea of time passing differently or a speed of light varying. These are variations in fundamental physics constants or parameters which we have tested for, and so far we found no evidence for. Time does pass differently according to the local gravity. That's a prediction of general relativity. But we see no indication that the speed of light varies or has any cosmic variation in different directions in the sky that we look.
David Gold would like to know, how was time dilation taken into account when calculating the current age of the universe as 13.8 billion years old?
Well, so time dilation is built into the calculation because the age calculation of the universe is done in an expanding Big Bang model, which is based on general relativity. So that, of course, uses the effect of gravity on time and uses sort of coeval measures of time to calculate an age. So it's essentially built into the calculation because we're using general relativity to make the calculation.
Robert Brady sent an email as a follow-up to a discussion we had in the last live session, where I guess you talked about gigatons or gigatons of antimatter that was most likely created in the Big Bang. So where did all this dark matter go? Or antimatter. Where did all this antimatter go?
So in the very early universe, the symmetry in the laws of physics was such that there were equal numbers of particles and antiparticles. And at some point, as the expanding universe cooled, the particles and antiparticles annihilated for the last time to leave behind radiation, and there wasn't sufficient energy in the radiation to create new antiparticles. And so at that point, the slight excess of particles over antiparticles would give us the universe of matter that we see. So that's where the antiparticles went. The universe essentially cooled sufficiently that the antimatter froze out by its annihilation with matter and then could not be recreated because there was insufficient energy.
The next question is from Miguel, who asks, he's on with us live, multiple sources of waves on a lake create a confusion of interfering waves. multiple sources of gravitational waves, or do multiple sources of gravitational waves create something similar? How can we identify a particular source in this mess of waves?
Yeah, it's a good question. So if you have a circumstance where there are multiple sources of gravitational waves traveling through 3 dimensions, then those waves they combine. It's interesting, however, they combine not by simple additive mathematics. So the waves of compression and rarefaction that correspond to sound waves combine additively, just a simple arithmetic calculation. Gravitational waves are tensor waves, however. Which means these waves have an amplitude that is different in different directions, in the 3 spatial directions. And so you have to use tensor arithmetic, not simple mathematical arithmetic, to calculate how gravitational waves add. But it can be done, and so a situation with multiple sources of gravitational waves, it's possible to predict how they would combine and then how you would detect them.
The next question comes from an email from Christina, who asks, she asks, how could we deflect a very fast-moving comet from a hypothetical collision course with Earth, and how difficult of a task would that be? So sort of like the movie that came out.
Right. So if we did find an object that we thought was on a collision course with the Earth, the nature of the warning system we have based on arrays of telescopes around the Earth that are tracking debris all the time, is that we would have several years' notice. So it would not be a dramatic 24-hour clock like Hollywood would want you to believe, where we only have a day or a week to figure this out. We'd have months or years, actually. And that's sufficient time to launch a mission. The hardware to do this is pretty clear. And then essentially the smart move, rather than destroying the object, which would release a lot of shrapnel traveling on the same trajectory and ending up in the same place, so that's not a good idea. The smart idea, of course, is to send a pretty massive spacecraft alongside it and use it as what we call a gravity tractor. So as you track the comet in its orbit at some small distance, the sheer mass of the spacecraft is pulling on the comet and slightly altering its trajectory. And if you do such a slight adjustment far enough out, you only need a very small deviation from its path to make it, easily miss the Earth. So that mechanism and the calculations of that are well in hand. We've done these kind of things before, so that's pretty much how it would work.
The next question is from Isla Holroyd, who asks, do all things fall at the same rate regardless of mass because gravity coupled to fundamental particles separately as if they were all identical?
Yes, the force of gravity, it's a universal attractive force, and so as the example on the Earth's surface, every object will fall at a rate of 9.8 meters per second, acceleration due to gravity caused by the mass of the entire Earth, and that acceleration rate is independent of the mass of the object. And so the gravitational acceleration is just a function of the mass of the attractor, and it doesn't depend on the mass of the particle that's falling in that gravitational field.
Excellent. The next question is from Richard Denizen, who asks, what are some of the major areas of inquiry the James Webb Telescope will be utilized to investigate given its greater resolving power?
The James Webb is going to do the things that it's built best for, because it's a large telescope, so obviously it can go very deep, very faint. It's good for looking far back in time and out in space. But it's also an infrared telescope, a near and a mid-infrared telescope. And so it's going to specialize in looking at things that it's hard to look at with visible light. And those include dusty star-forming regions, so it's going to look at objects that are buried in dust, like young stars, or dusty galaxies and their central black holes. And it will see through that dust and murk extremely clearly, especially because of its sensitivity with the huge mirror size. So that's something that it will do well. It will also be able to look at cool objects well, because cool objects emit thermal radiation in the infrared. And so it will be able to look at planets and cool objects like that, or brown dwarfs, very cool stars, and it will have way more sensitivity for detecting, say, brown dwarfs than any other telescope. So those are the things that it will do best. It doesn't actually have the sharpness of vision of the Hubble, because the diffraction limit is based on wavelength, and shorter wavelengths or bluer light have better higher resolution or smaller diffraction limits. So it's actually not as sharp an imaging telescope as the Hubble Space Telescope.
The next question is from Hernan Reyes, who asks, what is the exact definition for super-Earth exoplanets? And what is the main factor that will determine whether or not they can hold on to an atmosphere? Is it their size, their proximity to the star?
So super-Earth has never had an exact definition. The research groups that work on exoplanets have used varying definitions. And of course, it depends on how the planets are discovered, because we discover exoplanets through the Doppler method, which only gives mass, and then the eclipse method, which only gives size. So sometimes the super-Earth, the range of definitions includes things that are 30 to 50% larger than the Earth in size, or up to a factor of 2 more massive than the Earth. And those are sort of overlapping definitions. So there's no hard definition. There's a natural boundary, because there's a boundary between the size of a larger than Earth terrestrial planet and the point at which it turns into a small gas giant, such as Uranus and Neptune. So there's a natural gap there, but that goes well past the mass at which we think they might still be habitable. In terms of the likelihood that they have an atmosphere that could support life, anything up to twice the mass or size of the Earth is likely to have a very thick atmosphere, but there's no reason that it couldn't support life at the base of that thick atmosphere. The larger mass objects also will have more geological heating, and so quite likely to have tectonic activity, and that's also thought to be a prerequisite for life, although that's not by any means certain. So super-Earths are our prime real estate in terms of habitability and in terms of future life detection experiments.
The next question is from Harry Bell, who asks, in our universe, is cosmic expansion the result of space-time being stretched or created?
That's a good question. Formally, it's actually being created, because space-time is unfolding in a sense, and so when the universe expands, the space-time manifold, a manifold is a mathematical term for a sort of curved space in a mathematical sense, is indeed being created. So I think that's the right way of thinking about it, and it's being created from the vacuum. So the expanding universe was essentially borrowed from the vacuum of the infant universe, from vacuum energy, we think, and in the inflationary model, that source of that borrowed energy may have indeed been a quantum fluctuation, which is an extraordinary idea of how the universe actually came to be.
Excellent, thank you very much. The next question is from Parth Sarda, who asks, what is the current status of astrobiology and I guess the whole field of astrobiology? And can you talk briefly about the upcoming TESS mission?
Yeah, I mean, it's hard to, I'll treat those as two separate questions. The general status of astrobiology, that's a very big question in astronomy. I mean, it's hard to summarize simply because it's a big field. But given that the goal of astrobiology is to detect life beyond Earth, the status is that the field is in limbo, waiting for that first discovery. So there's increasing anticipation that the tools are now with us that are sufficiently powerful to be able to detect life beyond Earth, life on exoplanets or possibly in the solar system, but we haven't made that detection or discovery yet. So there's this increasing sense of anticipation that astrobiology is about to turn into a real field where we have other biologies to study except for the biology on Earth. The other part of astrobiology is, of course, the study of how life evolved and came to be on the Earth, and that's a continuing project because there's still things we don't know about how life started, or how inevitable it was that life has the form that we see around us. So that progress is happening fairly rapidly. And as a separate question, the TESS satellite. The TESS satellite was a natural complement to the Kepler mission. The Kepler mission was only looking at a small area of sky, about 170 square degrees, and 150,000 stars, and is staring at those for years on a time. And so the exoplanets that Kepler found, looking at a small area of sky quite deep, were hundreds or thousands of light years away. So all along, astronomers knew they needed a complementary mission that would look for exoplanets across the entire sky, but maybe not as deep and so more nearby. So TESS was designed to find nearby Earth-like exoplanets to complement the hundreds of more distant Earth-like exoplanets that Kepler found. And it's so far succeeding quite well in its job. It's still early in its mission, but it's going to produce some excellent candidates for future study with ground-based telescopes.
Excellent, thank you. The next question is from one of our live participants. Arturo asks, are there other effects of the moon on the Earth other than the tides?
Well, yes, the moon, the gravitational coupling between the moon and the Earth is of course creating, there's a conservation of energy and angular momentum principle involved. So the moon is actually gradually moving away from the Earth, and in terms of conservation of energy and angular momentum, that means the Earth is slightly slowing down in its spin rate. I mean, it's a tiny amount. It's like 1/1,000,000 of a second longer year per year, an Earth year, and the moon is moving away at about 4 centimeters per year. It's a measurable amount because we've put reflectors on the moon back in the Apollo days, so we can actually measure very accurately the distance to the moon. So that's a major effect, that over a long period of time the moon is going to retreat from the Earth, and the Earth is going to slow down in its spin, and at some point, very far off, in billions of years from now, the gravitational coupling of the moon that keeps it tidally locked will be relaxed, and the moon will start to detach itself from the Earth.
Excellent, thank you very much. The next question is from Jingsheng Li, who asks, what is your view on the Hubble tension problem? Is the local measurement more reliable than the CMB method?
So the Hubble tension is a phrase that's used to describe the fact that there's a disconnect or a difference or a discrepancy between the measurement of the expansion rate of the universe locally, that's the nearby Hubble constant measurement, and the one measured on cosmological scales going back to the Big Bang, and that's done using the microwave background, which references the time 400,000 years after the Big Bang. This discrepancy is at the level of about 5 or 6%, and that sounds small, but it's significant because the accuracy of the measurements in each case seems to be higher than that. It's not clear where the error likely lies. Ironically, even though you'd think that local measurement is more accurate or better determined or more reliable, it's not necessarily the case, because measurement of the local expansion rate depends on distance indicators that we have to use to reach out tens or hundreds of millions of light years to get sufficient samples of galaxies. And all the distance indicators have their own biases and systematic errors, and it's not clear that all of those errors have been understood. Microwave background observations have their own types of errors, typically more statistical in nature, the noise of the observation and so on. So at the moment, the jury is out. The Hubble tension has not gone away in the last few years as people have gathered more data. I don't know that the problem is hardened, but it's like people are now off looking hard at their data and their techniques and looking at systematic errors, because the history of astronomy is that many controversies or discrepancies or apparent problems in the end came down to unrecognized systematic errors.
The next question is from Faisal, who asks, why do visible light rays reach us from outside the atmosphere while infrared rays do not reach us, even though their wavelengths are longer and their frequency is lower?
It's a good question. The transparency of the atmosphere varies with wavelength, and it's basically to do with how those waves interact with the ingredients in the Earth's atmosphere. So what happens is that the longer waves of light, just going into the infrared, correspond to frequencies that are exactly around the frequencies with which molecules, particularly water vapor molecule in the atmosphere, oscillate or vibrate. And so that means those waves are going to interact strongly with water molecules and be absorbed by them or scattered. And so it's because of the way water molecules vibrate and oscillate at longer wavelengths and lower frequencies that infrared radiation is eventually allowed to penetrate them. So when you want to look through water vapor, you have to go either to a much longer wavelength, like radio waves, or to a shorter wavelength, like violet waves of visible light.
The next question is from Mark Harding, who asks, do we know if the elements resided somewhere in space or time prior to the Big Bang, or did the Big Bang create all of the elements?
The chemical elements have an interesting history. The Big Bang only was able to create the very lightest elements. It's the nucleosynthesis that occurred in the first 3 minutes, where the universe had a temperature of millions of degrees, and that was sufficient by fusion to create helium, deuterium, tritium, and lithium, and that's about all, because as the universe expanded and cooled, no higher levels of fusion were possible. So that's all the universe had in it after the Big Bang, and for the next few tens or hundreds of millions of years, until stars started forming. And then all the subsequent creation of heavy elements, including carbon, nitrogen, oxygen, and all the very heavy elements that are formed in giant stars and supernovae, were created in stars in the subsequent history of the universe.
The next question is from Basak, who asks, we consider exoplanets orbiting high-mass stars to not be habitable. But what if the organisms have much shorter lifetimes, that it's possible for evolution to be much faster?
Certainly that's a possible case, and so I agree that it would be foolish to completely rule out thinking of life around more massive stars. So the argument is that more massive stars have shorter lifetimes before they die, typically as a supernova very violently, and so it may not be enough time for life to develop. But we don't know how long biology takes to develop in general. We could say that because it took 4 billion years to go from the start of life to complex creatures and plants and animals like us, that we need that kind of time in general, but we don't know. It might happen 10 or 20 times faster under other circumstances. So yes, it would be unwise to rule out more massive stars to even think about for looking for habitable planets and life. But in general, we do think that having more time is favorable because of the Earth as the example of how it did take a long time to develop complex life. Remember, for 90% of the history of life on Earth, a very long history of life on Earth, there was nothing, no form of life that you could see without a microscope.
The next question is from an email. Hernan asks, Pluto was demoted, and rightly so, from being a planet in 2006. Now, with the discovery of thousands of exoplanets, has the definition of a planet been revisited, and if so, in what way?
No, exoplanet research has not caused anyone to revisit the definition of planet and dwarf planet. So the criteria that they used in the International Astronomical Union decision and the criteria that they codified in 2005 for a dwarf planet relative to a real planet, those remain in place. And so exoplanets are subject to this same distinction. Now, it turns out that we just know a lot less about the typical exoplanet, about their orbital situation and about their companions, or whether they might have been captured by their system and so on. So the dwarf planet distinction is not really in play for exoplanets just because of the kind of primitive state of our knowledge.
Excellent. Thank you very much. The next question is from Astro, who asks, I would like to know what you think about the Alcubierre metric or the Alcubierre warp drive for future interstellar travel.
So this is this was a scientist, a legitimate scientist, I think has some NASA credentials too, who developed a concept for a potential warp drive that involves distorting space-time around. The engine actually distorts space-time and essentially creates a sort of phase wave where you can go faster than light speed in principle. So it's an interesting mathematical construct that was used in the Alcubierre drive. This doesn't exist, of course. This is a hypothetical technology, and there's been a lot of debate in the literature about whether this technology could ever exist as a true technology, or even if the mechanism works at all. And the consensus generally amongst physicists is that it's not a legitimate way of generating faster than light travel. It has some interesting elements, but there's some weak places in the general chain of argument. And again, as a technology, it's not something we're anywhere close to being able to try and implement.
And it's kind of a follow-up question to that. One of the things I always wonder about this kind of technology, or these kind of hypothetical technologies, is shouldn't there be some kind of evidence that we can detect if people, alien civilizations were using this technology around us? Is there any hypothetical kind of detection method for ships using this approach?
Well, if there were the possibility of faster than light travel and this kind of a technology, and if it were in widespread use, then it would bring very strongly forward the Fermi question of where are they, as to be a real problem, because interstellar travel would be very easy and it would not take as long as we think it should take given the distances in the galaxy. So maybe the fact that we haven't detected intelligent aliens, or they're not widespread traveling across the galaxy visible to us, means again that technology doesn't really exist.
The next question is from Akshat, who asks, theoretically, what would a nuclear explosion look like in space, and what would possibly happen if that happened?
So a nuclear explosion just in the vacuum of space would, have some similar elements to what it would have on the Earth. The difference, of course, would be that most of the effect of the nuclear explosion in space would be pure just radiation. On the Earth, the effect of a nuclear explosion is, of course, massively amplified by the atmosphere, by the shock waves, and sort of incredible propagation of shock waves through the atmosphere. Pressure waves that can travel at hypersonic speeds and cause enormous damage. Well, there's no medium in interstellar space, and so essentially the radiation from an atomic explosion is all you get. It's just the radiation itself.
The next question is from a live participant. From our earlier discussion, why were earlier population stars so much larger than the present generation stars?
So it seems, this is all based on simulations because we don't really know. We have to use computers to see how this works. It seems that when you have a sort of primeval gas, which is the gas of hydrogen and just a little helium, you can actually form a star sequentially with a larger amount of mass. When you have gas that includes heavier elements, those heavier elements actually help cool the gas, and that accelerates the initial collapse, but it stops the initial collapse from going to much larger masses. So it's twofold. It's because the gas is pristine, hydrogen and helium, and it's also because the universe, of course, was very dense. If we're talking about a star that forms at a redshift of 30, that's when the universe was 30 times smaller and 30 cubed times denser, so enormously denser, and so you can just get a larger object forming because of that.
The next question is from Harry Bell, who asks, have neutron stars been detected in binary systems with other stars? Can this result in a type 1a supernova similar to a system involving a white dwarf?
Yes, neutron stars have been observed in binary systems, and even double neutron star systems have been observed. So you can definitely get this circumstance of a neutron star in a binary system that exists with a supernova having gone off, leaving behind a black hole or possibly another neutron star.
The next question is from Eva, who asks, related to the ninth dwarf planet, Sedna, are there any gravitational effects of Sedna on our solar system with a 10,000 year annual cycle?
No, for dwarf planets and all objects in the Kuiper belt. The Kuiper belt is the region between 40 and 80 astronomical units where Sedna and other dwarf planets that are similar in size to Pluto have been discovered and are anticipated. At that distance, for a small-massed object, there's extremely little gravitational influence on the planets of the solar system.
So then more generally, how far away can an object affect us gravitationally?
Well, gravity is an infinite range force, so in principle, gravity has its effect over very large scales. But we also talk about, in physics terms, a sphere of gravitational influence. So, for example, the Earth has a sphere of gravitational influence, and that dictates how far away an object can be to be in orbit of the Earth or to be primarily affected by the Earth. And then if you move further away, you enter the gravitational sphere of influence of the Sun. And this object, therefore, is being primarily driven by the Sun. And then beyond that, of course, then you're in the gravitational sphere of influence of the galaxy. So the way people calculate gravity, the force falls off as the inverse square law, of course, and it just depends on the realm or the size scale as to which object is governing the motions.
The next question is from Petra, who asks, what are your thoughts on dark matter existing as a result of black holes?
So black holes are a hypothetical explanation for dark matter because obviously they're dark in principle when they're not ingesting matter or in a low density environment. And we know that black holes exist in significant numbers in the universe. The black holes we've identified either at the center of galaxies, massive objects, or the dead massive stars are a tiny fraction of a percent. I think it's about 1,000th of a percent of the amount of dark matter. So they fail completely and miserably to account for the dark matter. However, there are also black holes that could form in the infinite universe, as when space-time was small and dense, and literally you could have the fluctuations in this high-density early universe creating miniature black holes. They're called primordial black holes because they form right from the Big Bang. And most of those black holes will evaporate. The smallest of them will evaporate by Hawking radiation, but there's an intermediate scale, a range where some small fraction of a gram black holes could persist for the age of the universe. And so there's a window of primordial black hole creation that could potentially account for the dark matter, because these will persist, survive, and there could be enough of them to match the amount of dark matter. At the moment, no detection of them has succeeded, and so they're not formally completely ruled out. But I think the odds that black holes account for the dark matter is a small odds at this point.
All right. The next question is from one of our live participants. Albi Prem John asks, as time is related to entropy, could time in any way be considered a form of energy?
Time is indirectly linked to entropy, so I don't think we can make a connection directly between time and energy. Time is only related to entropy in the sense that the arrow of time correlates with the way microscopic states behave and the number of equivalent microscopic states, which is the formal definition of entropy in physics. So it's a correlation, it's an indirect connection, it's not really a fundamental physical connection that would give time some attribute of energy.
The next question is from Richard, who's on with us live. Wouldn't it be more appropriate to quickly colonize the moon's dark side, as it is constantly shielded from solar radiation with frozen water and resources, before any attempt at Mars? What's your opinion on this?
Certainly colonizing or putting a long-term base on the moon, near side or dark side, is far easier and cheaper than colonizing Mars. I mean, just the difference in distance is phenomenal, and the energy cost of getting there. The moon, we're talking about a few days to a week. Mars, we're talking about 8 months to a year. So these are huge differences in time, distance, and energy. And yes, the dark side of the moon is a promising place to put a habitat because we know there's frozen water on the moon. We've found significant evidence of it. The Shackleton crater, for example, at the polar region has shadowed ice that has been directly observed, substantial amount of it. We're not so sure of the inventory of ice on the dark side of the moon, but again, in shadowed craters, it's likely to be substantial. So when there's water there, you have a lot of the raw material you need for a base because you have the water you would need to drink or to grow plants. You have water you can dissociate into oxygen and hydrogen, which will give you rocket fuel and oxygen to breathe. So yes, the moon is certainly a more plausible place to start a base than Mars initially.
The next question is from a user called Lunar, who asks, I've heard the term observable universe. Why is it that there are parts of the universe we cannot see?
It's because the universe expansion rate has changed since the Big Bang. And in particular, in the first 4 or 5 billion years after the Big Bang, the universe was expanding superluminally, which is to say faster than light, which means that any 2 points in space-time were moving apart faster than light speed, which may violate special relativity, does not violate general relativity, the theory that describes the expanding universe. So there's nothing like breaking a rule in physics because of this. But if the universe was expanding faster than light speed for some early period of expansion, that means there are regions that have been pulled away from us faster than light speed, and therefore light has not had the possibility to reach us from those regions. Now the universe did decelerate due to dark matter, and so regions that were initially moving away from us faster than light speed would subsequently slow down to be moving away from us less than light speed, and that means the light could eventually reach us. But it does imply that there are regions of the universe, substantial regions of the universe, that we have not seen, and we may subsequently see, but we can't see right now.
The next question is from one of our live participants that's kind of related to this. And the question is about objects moving faster than light. Do they have to have negative mass? If it's something is moving faster than light, would it go undetected?
The hypothetical faster than light object, a tachyon, it's a construct of physics. It again is a very theoretical concept. There's never been any observation of anything moving faster than light. Faster than light travel also implies a problem for causality, because you can have events preceding causes, which would be a rather remarkable situation. So I would say we're dealing purely in the realm of theoretical speculation, and the observable consequence of a faster than light particle is not clear, because we don't have a robust enough theory to make a prediction.
And the next question is from an email. What is the difference between cosmic strings and superstrings? And can you talk about what that object or those objects are?
So strings, in the normal way they're referred to, are regions, are sort of one-dimensional entities. They're sort of gravitational seams in the universe. That's the best way to describe it, because they're sort of high-density regions that cause gravitational lensing around them. So these are things that could result from the standard gravitational effects. Superstring is something else. Superstring is a hypothetical theory of unifying all the forces of nature, where the underlying entities that are part of everything we call a particle are actually tiny one-dimensional strings whose energy scale is 27 orders of magnitude smaller than the energy scale that unifies the weak and electromagnetic forces. So superstrings are a very unusual hypothetical ingredient of the universe that depend on unifying all the four forces of nature.
Excellent. Thank you very much. So the next question is about brown dwarfs. And the question is, if a brown dwarf is too small to sustain fusion of normal hydrogen, but can still accomplish less energy-demanding thermonuclear fusion of deuterium, how likely is it that it could live long enough and stay, quote, warm enough to allow life as we know it on Earth to develop on any habitable planet it might have orbiting around it?
So it's an interesting question. So brown dwarfs, there is a regime where brown dwarfs can have mild fusion. If you have a temperature of about 2 million degrees Kelvin, you can have fusion. You can have the first step of the three-step chain that leads the proton-proton chain that leads to the fusion of helium. So you have the first step of that, which is a fusion of a proton and a neutron into deuterium, and a small amount of energy release. But when you look at the energy release from the single-step deuterium reaction compared to the three-step hydrogen to helium reaction, it's more than an order of magnitude less. So this is a very feeble amount of energy. And of course, it won't last for very long, because gradually the star will radiate away that energy. It will collapse, but it won't ever be able to get to the higher temperature required to sustain other modes of fusion. And so eventually that deuterium fusion will just sort of give up slowly over time. So it's an unlikely scenario for supporting life on a surrounding planet, because the planet would also have to be very close because of that feeble amount of energy.
So then a related question is, what is the boundary between brown dwarfs and low-mass stars?
So the boundary is typically that of having fusion, a self-sustaining fusion reaction. And deuterium fusion is just the marginal existence of a stellar capacity. And the typical demarcation of a star is for the kind of nuclear reaction that the sun does, which is the sort of fusion of hydrogen all the way into helium in 3 steps. And that is the standard star distinction, which corresponds to about 7.5% of the mass of the sun, where that kicks in.
The next question is from Aditya Rao, who asks, what keeps neutron stars stable?
Neutron stars are kept structurally stable by the fact that they're just an entire, they're essentially an atomic nucleus with an atomic number of 10 to the power 57. So they are essentially pure neutron matter, where the neutrons are packed. You can visualize them almost like as eggs in an egg box or eggs in a carton. And they're kept close, and the only thing that keeps those neutrons apart at the distance they have is neutron degeneracy pressure, the quantum effect, where no 2 neutrons can have exactly the same set of quantum properties. So they're kept structurally stable by the fact they're as dense as an atomic nucleus, and they can still have structural instabilities because neutron stars are all spinning quite rapidly.
Our next question is from Mahesh, who sent an email. Can you talk a little bit about astronomy research and how recent research areas have used artificial intelligence in this field?
So astronomy is benefiting, as are all fields of science, from AI, and in particular artificial intelligence in astronomy is being used to accelerate the analysis of really large data sets. So astronomers use imaging devices to make enormous surveys of the sky, cataloging galaxies or stars or any manner of astronomical objects, and they have to digest this data and decide which of this large number of objects you might be able to see in an image are meaningful or relevant. And AI is a very powerful way to go through a training set based on the objects you want to detect, and then unleash it on the raw data, and it will find examples of those objects, and it will find them very flexibly in a way that you can be confident you're not missing anything. And of course it will do it without human labor involved, except in the calibration phase. So AI is proving very adept at refining astronomers' methods for detecting, cataloging, and understanding all manner of astrophysical objects.
The next question is from Steve Callender, who asks, in a lecture by Alicia Weinberger on the magnifies spectrograph, she mentioned that a planet was detected orbiting an Xray star. Can you talk about what an Xray star is? Are there stars that don't emit visible light?
Well, X-ray star is a term for stars that happen to emit a lot of X-rays. So these are still normal stars that emit a large amount of optical radiation, but the X-ray emission from stars is unusual enough that they get called X-ray stars. It just means they have proportionally a lot more X-rays than a star like the sun, for example. And what usually this means is these are stars, they tend to be massive stars. They're stars with really powerful chromospheres, so they have, which is the region of the star which has temperature of a few million degrees, and that's the temperature that leads to a lot of X-ray emission. So they're very dynamic atmospheres, active chromospheres, and hot spots, of course, that create a large amount of X-ray radiation. And they're interesting in that regard because they're very active stars.
The next question is from a live participant who asks, how does synchrotron radiation occur?
Synchrotron radiation results from the acceleration of an electron in a magnetic field. So, and at a relativistic speed, or speed close to that of light. So when an electron moves through a magnetic field, the coupling of the electrical charge of the electron with the magnetic field leads it to gyrate, or travel in a spiral typically. And if it's at a slow speed, that electron, as it moves, it's accelerating, and so it releases radiation from its acceleration because it's traveling in a circle. That would be cyclotron radiation. And cyclotron radiation is, of course, used in physics all over the place. There are many labs where cyclotron radiation is a tool for medical research and so on. Now, if that electron is moving at a relativistic speed, speed close to that of light, the radiation that normally is emitted in a large range of directions becomes forward focused in a beam, and it's much higher energy proportionally because the electron is close to the speed of light, and that becomes synchrotron radiation, and that's what synchrotron radiation is. And synchrotron radiation in astrophysics is typically marked out by the fact that the radiation is polarized, and that polarization reflects the magnetic field that the electron was traveling in.
All right, I think we have time for just a couple more questions. Jerry Salazar asks, what is the method used to determine Earth's distance from the sun on any given day?
Well, it's a good question because it's a sort of very basic thing in astronomy, the astronomical unit. So the astronomical unit, or the distance from the sun of the Earth, was first detected and first measured a couple hundred years ago, and it's measured by trigonometry, of course. So we can set up a situation where we have observations from different parts of the Earth's surface and observe the sun at a coordinated time, and then develop that little triangle and calculate the angle, and that gives you the distance. So that's how the AU was first measured, and that's still how the astronomical unit can be measured. Now, our ability to do it now is hundreds or thousands of times better than it was a few hundred years ago, and so our measurement of the AU is quite precise now. And it's, of course, part of the fact that we know that the Earth is in an elliptical orbit of the sun, and so we know how that orbital speed and distance from the sun changes over a year.
All right, and I think this will be our last question for today from Parth Sarda, who's on with us live, who asks, how is time related to the Higgs boson, as the Higgs field interaction gives us the notion of mass, which interacts with time?
Well, it's an interesting question. If there any relationship at all, it's not clear. So the Higgs mechanism, the Higgs boson, is indeed what attributes or ascribes mass to fundamental particles. But mass and time are not directly coupled in any physics sense. Time is coupled to space through general relativity. But mass affects time only in that indirect sense that the local gravitational field obviously impacts time. But at the level of the attribute of a subatomic particle, there's no obvious sense in which time is affected. So I think at the level of the Higgs particle, time is essentially decoupled from the mechanism. So thanks. Variety of questions. That's great as always, and we'll announce our next few live sessions soon. And thank you for your questions. Thanks to Matthew for facilitating, and Vicky behind the scenes as well, I think.
Yes, she is. She's been helping us grab questions from the chat. So thank you all very much for joining us today. We appreciate you coming and spending your time with us today, and we will see you in just a couple weeks. Take care, everyone.